Okay, now recording. All right, now, as I think I mentioned in my email and Canvas announcements, even though we didn't meet yesterday, you're still responsible for that little mini video. Okay, I'll give you the highlights quickly on it. Okay, so from that mini video I gave you yesterday, so again, even though we didn't meet, you were supposed to watch it, and that's the quote unquote lecture. Therefore, I'm completely done with 3.5, and I'll start 3.6. Okay, so I'll do 3.6 today and tomorrow, and again, end of class tomorrow, you have a quiz. Quiz will be on all derivatives, pretty much everything that we've had so far. Okay, so I'll ask you, some functions, and you just give me the derivative. Okay, might be, product root, quotient root, chain root, trig, inverse trig, exponential, logs, which we're about to do, and stuff like that. Okay, for tomorrow's quiz. All right, let's see. There's a chance that I can let you have some question and answer time today, but I'm not promising that. Okay, so if you have questions from yesterday's stuff, because we didn't meet, I just had to throw together a video. If you have any questions, I might be able to give you time at the end, so think about that, but I'm not promising I can do that. Okay, I need to make sure I cover all the material that I wanted to. Okay, so if you watched yesterday's video, then I'm done with 3.5. Okay, and really very quickly hitting the highlights was the inverse trig derivatives on page 214. So inverse sine, cosine, and tangent. Never mind about cosecant, cotangent, and secant. Okay, so put these on your next cheat sheet. Inverse sine's derivative, 1 over radical 1 minus x squared. Inverse cosine is the same thing except for a negative. Inverse tangent, 1 over 1 plus x squared. So that's what yesterday's video covered. In case you didn't watch it, you can still watch it, obviously, anytime. And then there was some chain rule involving that. Okay. So again, you are responsible for that material, and sometimes there's a tendency, if the teacher says, "Oh, class is canceled," then you say, "Okay, it's a mini holiday." Well, not really. You're still responsible for everything I did yesterday. But I realize you may have some questions about it. So if I have time, that's a big if, then I'll do some problems involving this or any other section. But I do need to get started with 3.6 now to keep on schedule. Okay, so 3.6 is on log functions, page 218. Okay, and I'll give you the derivation of that. Okay, so schedule-wise, we're still okay because I gave you the mini video yesterday, and hopefully you watched it. So 3.6. Okay, we're aiming for about 3 sections a week. So 3, 6, 9, and then 10 and 11, and then the test, and then we have our spring break coming up very shortly. Okay. All right. So 3.6. Question is, what is the derivative of natural log of x, ln x prime? Okay, so I'll go over the derivation again. So this is another one of those where I'm responsible, but you're not. So if you want to, again, not pay attention, tune out for about a minute, it's okay. But some of you might be interested, where do they come up with this rule? All right, so we write y equals natural log of x. We exponentiate both sides, put an e here and an e here. That way, e to the ln x just becomes what? X. E to the y equals x. Then we differentiate implicitly. Okay, you might, those of you that saw the video, hopefully, to prove the derivatives of inverse sine, cosine, and tangent, we change it to sine, cosine, and tangent and did implicit differentiation. And once again, all those derivations from yesterday's video on the inverse trig functions, you're not responsible for any of the derivations. I'm responsible for the derivations, but some of you out there might be saying, where do they come up with that? So maybe, so you say to yourself, maybe I don't understand everything that my teacher did, but at least he showed us, oh, that's how you come up with the derivative of inverse sine, cosine, and so on. So same kind of thing over here. Okay, so e to the y equals x. Now differentiate implicitly. Okay, so the derivative of the left side is e to the y times dy dx, because there's a y involved, right? Derivative of the right side is 1. Divide both sides by e to the y. So dy dx is 1 over e to the y, but e to the y is equal to x. So we have 1 over x. So that's the derivation of the derivative of natural log of x. So time to pay attention again, so to speak. Okay, and what you're responsible for, put this in your next cheat sheet. The derivative of the natural log function, natural log of x, 1 over x. Derivative ln x is 1 over x. Okay, so it's not that bad. It's not as easy as e to the x. Derivative of e to the x is e to the x, but the derivative of natural log of x is 1 over x. Okay. Page 218, box 2. There it is. The derivative with respect to x of natural log of x is 1 over x. Okay, and as you might guess, all the chain rules apply. All of these can have the chain rule, right? Like even yesterday's video with the inverse trig functions, there's chain rule involved with that too. Okay, so derivative of ln x is 1 over x. The next thing I want to show you is what happens if you have a log to any other base. Ln x means log base e. How about log base 2, log base 10? Okay, they have their derivatives, but it's not as nice. So I'll show you how that works. Suppose you have y equals log base b of x. What's the derivative? Okay. Well, you might recall from algebra that you can write log base b of x as ln x over ln b. That's one of the properties, the change of base property. Okay, if I sneak in a 1, then 1 over ln b is a coefficient. B is considered a constant. It'd be like 7, pi, 10, or something like that. Okay, so from algebra, I can rewrite this as ln x over ln b. So therefore, y prime is, this is a constant multiplier root. Okay, so if you have a constant times a function, the derivative is the constant, 1 over ln b, times the derivative of the function. And now that I've written this in terms of natural logs, I now know the derivative of ln x is 1 over x. Okay, and writing this a little bit cleaner, 1 over x ln b. Okay, so put this on your next cheat sheet. See, there's sure a lot of derivative shortcuts. Yeah, don't forget we have 11 sections and we're only about halfway through. We're getting all the shortcuts, but keep in mind, it's a lot better than for us to keep doing limit h approaches 0, f of x plus h minus f of x all over h, right? Okay, so derivative ln x. So our favorite base is base e, the natural log. Derivative is 1 over x. If you have log base b of x, 1 over x ln b. So it's clumsier. Right, so what's the derivative of log base 10 of x? 1 over x ln 10. How about log base 2 of x? 1 over x ln 2. So again, it's clearly not as nice. It's clumsy to have any other base than base e. Okay. Can I still use this rule with base e? Yes, you could. Log base e of x by this rule is 1 over x ln e, but ln e is 1. So we get the same thing. Okay, so let me show that to you in the text also. So page 218, this is box number 1. Clearly not as nice. The derivative with respect to x of log base b of x is 1 over x ln b. Okay. So log base 7 of x, the derivative is 1 over x ln 7. What's the derivative of log base pi of x? 1 over x ln pi. So you have to keep putting that ln there extra, which of course we don't like. Okay, and now at long last, we can finally prove the power rule, okay, which we introduced way back in the first section. We know the derivative of x to the n was n x to the n minus 1, okay, and that works for all real numbers. Okay, so way back several sections ago, we said, well, we'll just accept it without proof now, but maybe we'll prove it later. This is the later. Okay, so how do you prove it? And this is for all real numbers. Now, back in chapter 2, we did the limit definition, right? Limit h approaches 0, f of x plus h minus f of x all over h, and saw the derivative of x squared was 2x, derivative of x cubed was 3x squared, derivative of x to the 4th was 4x cubed. That was the last question on the test, you might recall. Okay, but how do I know it works for any real number? Big, small, positive, negative, fractions, decimals, and so on. Okay, so here's the mini proof of that. So again, you can tune out for a little bit if you wish, since I'm not holding you responsible for this. You are responsible for knowing the result right here. Okay, but some of you might want to know, where does it come from? Okay, if I take the natural log of both sides, ln y equals ln x to the n. Okay, a property of log says I can bring the n down in front. So ln y equals n ln x. I now differentiate implicitly on both sides. So this implicit differentiation is a common theme here. So 1 over y dy dx equals n is a constant, so n times 1 over x. Okay. Solve for dy dx, multiply both sides by y. Okay. So dy dx is n y over x. Okay, but what was y? Y was x to the n. So n x to the n divided by x. X is like x to the 1. And x to the n divided by x to the n divided by n to the 1 is n x to the n minus 1. So there we go. Okay, so pay attention again. Okay, so this proves that the derivative of x to the n is n x to the n minus 1. Okay, now this technique we're going to be doing something called logarithmic differentiation. Okay, so you don't really have to worry about it here, but we are going to have this topic in this section, something called logarithmic differentiation. You don't have to write that down. It's going to be in the text later, and I'll write it further down the line. Okay, but this is now a little proof that the derivative of x to the n is indeed n x to the n minus 1. Okay. In short, everything that I've shown you so far, what are you responsible for? This and this. And well, you already know the power root. I was responsible for showing you the proof. What's the derivative of x to the n? N x to the n minus 1. Okay, and let me just raise it up again for focusing purposes if you want to look at the video later. Again. All right, so there we go. All right, so we're ready to start some of the problems. So what was on the homework? So we have 3 to 33 odd, 39 to 51 odd. So we have to go up to 51. Take a look. Page 223. Okay, so for the benefit of those of you that don't have the book and aren't getting it, and that, and that, and that. There's that theme again, find an equation of the tangent to the curve. Okay, anything with that graphing calculator icon, skip, like 35, 36. See above problem 39, or see where it says 39 to 50, use logarithmic differentiation. Okay, when I show you the derivative of x to the n, I was doing logarithmic differentiation, and I'll show you how to do those kind of problems too, hopefully. And that should do it. Okay. All right, so here we go. Okay, question 3. F of x equals sine natural log of x. Number 3. What's the derivative? Okay, now be careful. This is not a multiplication. So you don't do the product root. It would be the product root if it said sine x ln x. But it's sine of ln x. So it's a composition. This is the inside function. This is the outside function. This is the inside function. Okay, so how do I differentiate sine? Cosine. So f prime of x is cosine ln x. And then by the chain root times the derivative of the inside function, which is 1 over x. So final answer, cosine ln x over x. Okay, and once again, this is not, it's not a product root. You'd have to have an extra x there. So it would have to say sine x ln x in order for me to make it into a product root. But this is a composition, sine of ln x. So think of it as sine of something. So you go cosine of something, ln x, times the derivative of the inside, 1 over x. So cosine ln x over x. Okay, 5. And the next one I was going to show you is 9 and 13. Use properties of logs whenever you can. Okay, so what do I mean by that? Number 5, f of x is natural log 1 over x. Okay, now, if I just go straight by the letter of the law, I got ln something, right? So you could differentiate by going 1 over that, 1 over x, and then times the derivative of 1 over x. Kind of clumsy. Much better is before you take the derivative, remember that 1 over x is x to the negative 1, right? And then I have a property of logs that says that negative 1 gets to come in front. So even before I start, f of x is equal to negative natural log of x. So the coefficient is negative 1. Now that's real easy to take the derivative. F prime of x is negative 1 over x. So that's it. So you can see it's a lot faster, way faster than trying to take it exactly as written, where you'd have to go 1 over whatever's behind my pen, 1 over x times the derivative of 1 over x. This is a lot faster. Okay, so use the property of logs. Okay, a quick word again, whenever you're taking a derivative, use a derivative symbol. Okay, so if you don't, I could take off points for that. And here's what I mean. Sometimes I see students, let's say you don't write this f prime of x, and you just kind of put equal. Somehow equal is like a connector between statements. So you write that and that and that, and then equals negative 1 over x. Right? So I get students that would sometimes go like this: ln 1 over x equals ln x and negative 1 equals negative ln x. This is true, this is true, this is true. And then equals negative 1 over x. That is not true. Show this to any algebra 1 student. And it's, you know, you wrote negative ln x is equal to negative 1 over x. That's not true. We know that's not true. Now I know what you did. You took a derivative. Okay, but you can't just keep putting equal anywhere, as if equal is just some kind of connector. It's like a period, writing your English essay or something like that, right? No, give me some derivative symbol. So f prime of x. Now this is a true statement, right? But if you don't put f prime of x or y prime or dy dx, right? Then you're saying this is equal to this, true, is equal to this, true, is equal to this. That's not true, right? So I'm allowed to take off points if you don't write mathematics properly. It has to be written correctly. I know what you did. You took a derivative, but you got to write it properly. This is not equal to that. The derivative of this is this. Okay, this was derived from here, hence we say the word derivative. But again, the verb form is differentiate. Okay, we differentiated this function to get this. Okay. All right, I'll show you another problem where you definitely want to use properties of logs. That would be number 9. So when you have logs, ln in particular, take advantage of your properties of logs. Okay, g of x is ln x e to the negative 2x. Now, recall from algebra, natural log of a product, ln of ab, is the sum of the logs, we say, is ln a plus ln b, right? So the hard way to do this, you could do it, but it's very clumsy. You could do the chain rule. The outside function is a natural log function, right? So you could take the derivative as y prime is 1 over this, 1 over x e to the negative 2x, and then times the derivative of the inside, whereby you'd have to do the product rule and a chain rule. Very messy. Okay. Instead, much better, properties of logs, ln of something times something. So how about ln of the first, ln x, plus ln e to the negative 2x, right? ln of a times b, ln of ab, is ln a plus ln b. And furthermore, what do you notice about the thing I have circled? Can I do anything with that? ln e to the negative 2x. What do you think that is? Negative 2x. The ln and e cancel out. Anytime you have an ln and an e back to back, ln with an e or e with an ln, if you have an e and an ln, it's normally e raised to the ln. They just cancel each other out. They are inverse functions of each other. So look at how easy this function becomes compared to if I just took it literally from here. You'd have to go 1 over that times the derivative of the inside, which is a product, and there's a chain rule. Right. Now differentiate that. Okay, notice the notation. G of x equals, this is equal to that, equals, this is equal to that. But the next step, I'm taking the derivative. So g prime of x. You cannot just say equals, right? So g prime of x. So derivative of ln x is 1 over x minus 2. And that's it. Right. So whenever you can do properties of logs, you should do properties of logs. And that was a perfect example there. And next one I'm going to show you is also like that. 13 was pretty bad. In fact, it's so bad I even had a hard time writing it. G of y is natural log of 2y plus 1 to the 5th power divided by square root of y squared plus 1. Maybe it's better if I just show you what it was originally in the book. 13, ln 2y plus 1 to the 5th over square root of y squared plus 1. Now, if you do not use properties of logs here, it gets real bad. Okay, so you definitely want to use your properties of logs for this one. That's a 5. Not sure that helped you. All right, I have ln of a quotient. What is natural log of something divided by something? It's ln of the top minus ln of the bottom. So ln 2y plus 1 to the 5th minus ln, square root means raising to the 1/2 power. And guess what I get to do with a 5.5? They both come down in front. Makes it much nicer. So 5 natural log of 2y plus 1 minus 1/2 natural log of y squared plus 1. And the problem becomes much, much easier, way easier. All right, so g prime of y. How do I differentiate 5 times ln? It's 5 times, okay, the derivative ln of something is 1 over that, 1 over 2y plus 1. Then by the chain root times the derivative of the inside. So what's the derivative of 2y plus 1? 2. Minus 1/2. Derivative of natural log y squared plus 1 is 1 over y squared plus 1. And again, by the chain root times the derivative of the inside, which is 2y. Okay, and then just clean it up. On top, I have 5 times 1 times 2, which is 10. And let's see, I have negative 1/2 times 2, 2 cancels out. So y over y squared plus 1. Okay, and yeah, let me raise it up again for focusing purposes, in case what I showed you was too blurry. Some more here. I'm about to do 17 and some other stuff. Okay, 17. T of z is 2 to the z log base 2 of z. Okay, and just to let you know, I will draw my z's with a little mark through it. Notice if I don't put it, then my z's end up looking like 2's. So there's a nice contrast here, I guess. Okay, you know how if you write something real quickly, right? You go like that. So is that a z or a 2? Right? So if I really want a z, I'll go like that. I'm frankly too lazy to make sharp corners like so, right? Like it should be. That takes too long. So my z's will always have that little mark there. In fact, if you take a look, if I didn't put that, you might say, well, it kind of looks like a 2, right? So my z's will always have that. Okay, so I don't like this because 2 here and a 2 here. So I have to remember, how do I differentiate if the base is not e? So again, our favorite base is base e. We don't like base 2. And furthermore, there's a product. So I have to do product rule. So here we go. First function times the derivative of the second. So what's the derivative of log base 2 of z? That's a new one. That's 1 over z ln 2. Page 218, box 1. The derivative of log base b of x, 1 over x ln b. So log base 2 of x, derivative is 1 over x ln 2. Or 1 over z ln 2. Okay, first function times derivative of second. F g prime plus g f prime. So copy the second function, log base 2 of z, and then times the derivative of the first function. So what was the derivative of 2 to the z? 2 to the z natural log of 2. Again, it's clumsy, definitely not as nice as base e ln. Okay. And just a little bit of touch up. That times that, 1 times that is just 2 to the z. So I put the final answer as 2 to the z divided by z natural log of 2. And then this one, I just put this in front. That's the normal place to put it. So 2 to the z log base 2 of z natural log of 2. All right, I'm going to take a little bit of a timeout to show you something else. Okay, we now know the derivative of natural log of x with respect to x is 1 over x. What's the derivative of natural log of negative x? That's going to be chain rule, right? So first you go 1 over negative x times the derivative of the inside. What's the derivative of negative x? Negative 1, which also comes out to be 1 over x. So what am I trying to show you? The derivative of natural log of x is 1 over x. The derivative of natural log of negative x is 1 over x. Therefore, I can make this conclusion. Okay, and frankly, we're not going to need this that much now. We are going to use it a lot more in our last chapter, chapter 5. Okay. The derivative with respect to x of natural log of absolute value of x is 1 over x. Granted, there aren't that many homework problems that involve this now, but later on we will. Okay, but just make a note of that, keep it in code storage. But the derivative of ln absolute value of x is 1 over x. Now, how can I conclude that? Okay, you might recall absolute value of x can be defined as either x if x is greater than or equal to 0, or negative x if x is less than 0. Okay, as a definition of absolute value. It's either the same thing if it's positive, in which case I have this. But absolute value of x is the opposite of x if x is negative. So I have this. But in either case, the derivative came out to be 1 over x. So now I can say the derivative of natural log absolute value of x is also 1 over x. And if you want to see where that is in the text, page 220, box number 4. Derivative with respect to x of ln absolute value of x is 1 over x. The comment Mr. Stewart puts above, the result is worth remembering. Again, that's true. Again, if we were meeting face to face, I'd make you memorize it. Okay, so just keep that in mind. Maybe your next calculus teachers might force you to memorize it. So be that as it may. Okay. And again, we aren't going to have that many homework problems right now involving that, but we will when we get to chapter 5. Okay. Oh, and there's that logarithmic differentiation that I'll be talking about shortly. Shortly might not even be today, it might be tomorrow, but we'll see. Okay. So example 25, y equals ln absolute value of secant x. Okay, truth be told, if I had parentheses, I would do the exact same thing. Okay. But we now know if you have ln x like this, the derivative is 1 over x. But if you have ln absolute value of x, the derivative is still 1 over x. Okay, so you just do the same thing. So say 25, y equals natural log absolute value of secant x. And what do I do with the absolute value? Don't worry about it for now. It's the same derivative if I have parentheses. Okay, so how do I differentiate ln? You go 1 over. So 1 over secant of x. And then by the chain rule, it's times the derivative of secant x, which we now know to be secant x tangent x. Put it on your cheat sheet. Yes, if we met face to face, I'd make you memorize it. And then secant x just cancels out. So y prime is just tangent x. So they ask for the second derivative. That's easy. Y double prime is just derivative of tangent x, secant squared x. Okay, and let me go ahead and give you a focus on all of these. Raising it up so you can see it better. I'll look at the video. I'll get to some of these later. There's that logarithmic differentiation thing. Get to that and some of that and some of that. Okay. 33. Y equals ln of x squared minus 3x plus 1 at the point 3, 0. So recurring theme, right? 33, find the equation of the tangent line to the curve at a given point. You see that over and over and over again. So we're going to put it in the point slope form. They already give us the point 3, 0. We just need the slope. How do I find the slope? Derivative. Then throw it into y minus y1 equals m times x minus x1, and then generally stop after that. Okay, so natural log of x squared minus 3x plus 1 at the point 3, 0. By the way, they didn't have to give you the 0. What happens if they only give me the 3? Well, I just plug in to get the 0. All right, let's try it. Put a 3 here. 9 minus 9, 0, plus 1. So I'll be taking natural log of 1, and that does come out to be 0. Okay, so they don't have to give you the y coordinate. If they don't give you the y coordinate, then just plug in. Okay. And that says x1, y1. So we already have the 3 and a 0, 3 and 0. I just have to figure out the slope. Slope means derivative. So what's the derivative of this thing? So it's ln of something. So you go 1 over that, right? 1 over dy dx is 1 over x squared minus 3x plus 1. And then by the chain roots times the derivative of the inside, which is 2x minus 3. And normally we just slide that over there. So 1 times 2x minus 3. So derivative is 2x minus 3 over x squared minus 3x plus 1. Now they tell me at 3, 0. So I plug in 3. So what do I do with the 0? Well, if I see any y's, I plug in 0, but there are no y's. Okay. So the y's would tend to show up when you have the implicit differentiation, right? Remember, we had x's and y's all mixed together. Okay, so I just plug in 3. 2 times 3 minus 3. 3 squared minus 3 times 3 plus 1. 2 times 3 is 6. 6 minus 3 over 9 minus 9 plus 1. 3 divided by 1, 3. Slope, point. Y minus y1 equals m times x minus x1. That's the equation of the tangent line, and we can stop.
Excuse me, Professor.
Yes.
You were saying earlier that if you weren't given the y coordinate, you could plug in x to find the y coordinate. Do you plug that into the original equation that they give you?
Correct. So to find a y coordinate, don't plug into the derivative. That'll give me the slope. Plug back into the original right here. So suppose they only said x equals 3. And so how do I find y? Then I just plug in. I think we've seen examples like that before, but we'll probably have more. So the language might be find the equation of the tangent to the curve, blah, 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 at x equals 3. And that's all they say. They don't give me the y coordinate. Then yeah, plug into the original, not the derivative, but the original to get the y coordinate. Yes.
Thank you.
Okay, you're welcome. All right, introduce logarithmic differentiation. What time is it? Not sure how much time I can give you for questions and answers, maybe none, but we'll see. Logarithmic differentiation. Okay. Now, before I do logarithmic differentiation, look back at question 13. It was nice because I had the ln. Okay. If I did not have the ln, it'd be very messy. I would just have a quotient rule and, it's just not even nice to look at, right? Quotient rule, and you got to do a chain rule and something to the 5th power and a square root. Pretty bad, right? It's almost as if to say, yeah, let's take a look at, say, 41. 41, you kind of wish you could say, I wish I could cheat and change the problem to be like 13. And I wish I could just sneak in an ln in front, right? Am I allowed to put an ln in front? See, if I put an ln in front, I can start using my properties of logarithms and make it nicer just like problem 13. Okay. You say, well, you can't just change the problem and put ln in front. Well, there's an equal sign here. So let's dig deeper. I can put an ln here if I'm also willing to do what? ln on this side, right? You can take the natural log of both sides. That's the essence of logarithmic differentiation. In fact, I use that trick when showing you the derivative of x to the n. When I said you didn't have to pay attention, okay? You can pay a little bit of attention now. I took the ln on both sides because then I could take the properties of logs and bring that n down. Okay, so you start off by taking natural log of both sides for something called logarithmic differentiation. Okay, the logarithmic differentiation problems are 39 through the n. Okay, and let me show you in the text the steps in logarithmic differentiation, page 221. Okay, I'll leave it up to you if you want to write that down or not. Okay, again, if we were meeting face to face, you wouldn't get to write it down, you'd have to memorize it. Okay, maybe you don't have to write it down if you just kind of understand the principle. Okay, you take the natural log of both sides and then use the laws of logarithms. Do implicit differentiation and then solve for y prime or dy dx. Okay, so I know I ran through that quickly, but I think I'd rather just show you some examples of how that works. It's on page 221. If you want to put this entire box on your cheat sheet, you may. I don't think you have to. It's correct, but you take the natural log of both sides, do implicit differentiation, and then solve for dy dx. Okay. Usually what happens if we met face to face, like the last time I taught face to face, you know, usually students will look at this and say, I have no idea what's going on. And then once I show some examples, they say, okay, I know what's going on. I don't even have to write this down. I just know what to do. So I'll try to get you to the point where I know what to do and you don't even have to write any of this down, which is exactly what I would have made you do had we met face to face and you don't even get a cheat sheet and so on. Okay, so let me see if I can illustrate that principle. Okay, so 41. Y equals a real messy square root. X minus 1 over x to the fourth plus 1. So the game I'm playing is, I wish there was an ln in front. Well, put the ln. That's not fair unless you ln both sides. Okay, that is basically step one. Take natural logs of both sides. Once I have the ln, then it says use the law of logs to simplify. Okay. So rather than differentiating from the get-go, right here, right? You'd have to go blah, blah, blah to the 1/2, and that's a mess. 1/2, all of this at a -1/2, times the derivative of the inside, which is a quotient rule and a chain rule. Don't like it. Okay. Take logs of both sides, ln both sides, which means I can write this as blah, blah, blah to the 1/2. Now that there's an ln here, what happens to the half? Come in front. How do I do ln of a quotient? Ln of the top minus ln of the bottom. So now I have natural log of y equals 1/2 bracket natural log x minus 1 minus natural log x to the fourth plus 1. This is much, much easier to do, believe me. Okay, differentiate implicitly. Number 2, differentiate implicitly. But the left-hand side is always going to be the same thing, okay, as we shall see. So what's the derivative of ln y? 1 over y times dy dx. It's always going to be that way. You can pretty much just bank on it. Okay, what's the derivative of this? So constant multiplier, right? If you have 1/2 times something, the derivative is 1/2 times the derivative of the inside. So what's the derivative of ln x minus 1? Well, 1 over x minus 1 times the derivative of x minus 1, but that's just 1. So 1 over x minus 1 times 1 minus, what's the derivative of natural log x to the 4th plus 1? I'm going to go 1 over x to the 4th plus 1 times the derivative of the inside for x cubed. So there we go. So right now I have 1 over y dy dx is equal to 1/2 bracket 1 over x minus 1 times 1. If it's times 1, you don't have to write it. Minus 1 over x to the 4th plus 1 times 4x cubed. Now, look on the left-hand side. You want to isolate dy dx. So how do I isolate dy dx? Basically, get rid of 1 over y. How do you get rid of 1 over y? Multiply by y. Okay, so multiply y on both sides. But in your final answer, dy dx, don't write it as y. Write what it was equal to. What it was originally equal to was this mess, this square root, right? So the best way to write the final answer is 1/2. Here's the y. Normally we sneak it back in front. So 1/2 that y radical x minus 1 over x to the 4th plus 1 times this new stuff. 1 over x minus 1 minus 4x cubed over x to the 4th plus 1. Okay. That was part 3, which says solve the resulting equation for y prime. Basically, you just multiply both sides by y. It's always going to be that way. Okay, and hopefully this will become more evident as we do more and more problems. Okay, so let me quickly summarize what happened, the process of logarithmic differentiation. Okay, so we had y equals blah, blah, blah. So just overall big picture, take the natural log of both sides. So the left side's ln y, right? Then use your property of logs to simplify the right side. So what I did was write blah, blah, blah to the 1/2. Then I said, oh yeah, the half can come down in front. I have ln of a quotient. I know what to do with that. Ln of the top minus ln of the bottom. So now when I differentiate, it's a much easier problem. The left side becomes 1 over y dy dx by implicit differentiation. It's always going to be that way. And then I did the derivative of the right-hand side. There's no y involved, so you don't have to put anything extra. So 1 over y dy dx is all this. And then how do you isolate dy dx? Multiply both sides by y. Okay, so that cancels out. Dy dx is 1/2. But in your final answer, don't write y. Write what it was originally equal to. It was originally, in this case, equal to square root of that mess. So I just copy that, 1/2 square root of blah, blah, blah. And then I have this extra factor. All right. Okay, then I'll show you all this other stuff here too. The other main instance of logarithmic differentiation, okay, is if you have, look at 43 and on, you have a variable to a variable expression to a variable expression, like 43 x to the x, 45 x to the sine x, 49 tan x to the 1 over x. Those are also cases of logarithmic differentiation, okay? So let me do a little summary here, and if you want to put this on your cheat sheet, you may. So again, you're getting a nice advantage as opposed to meeting face-to-face because I make you memorize all this. But something involving exponents. Okay, so what's the difference between all of these, right? Because it's easy to confuse these. If you have a variable to a constant, like y equals x squared, variable to a constant, okay, that's just going to be the power root. So y prime is 2x. Okay, if they switch it, constant to a variable, 2 to the x, do not do the power root. In other words, don't go x 2 to the x minus 1. No, this is an exponential function. So constant to a variable, y prime is 2 to the x ln 2. The next case is if you have a variable to a variable, like problem 43, x to the x, variable to a variable, then you must do logarithmic differentiation. Okay, so like 43. So Same thing. So watch out. Do not go x to the x minus 1, like a power rule. Okay, so the power rule only applies if you have something like this: variable raised to a constant, x squared, variable constant, then power rule, 2x. Okay. Switch it. Suppose you have a constant to a variable. That's an exponential function. So don't go x to x minus 1. Derivative is 2 to the x ln 2. If you have a variable to a variable, x to the x, then do this logarithmic differentiation. Okay. Yeah, I'll just mention quickly. You left out constant to a constant. That's easy. How do you do a constant to a constant? Like, what's the derivative of 2 to the 50th power? I think we had a problem like that, right? What's 2 to the 50th power? It's still another constant. So the derivative is 0. So that's why I didn't put constant to a constant on the list. It's still a constant. So derivative is 0. Okay, so let me show this to you quickly and then we're done. I guess I don't have time to give you a question and answer session, sorry. But be that as may. So y equals x to the x. Don't do the power rule. Instead, logarithmic differentiation, ln both sides. ln y equals ln x to the x. As soon as you do that, x gets to come in front. I don't want that x floating up there. I want it down in front. So ln y equals x ln x. Okay. Implicit differentiation. Truth be told, the left side's always going to be the same. It never changes. 1 over y dy dx. You can pretty much take it to the bank. 1 over y dy dx. Okay, this is a product rule. First times the derivative of the second, derivative ln x, we now know is 1 over x. Plus second function ln x times the derivative of the first, the derivative of x is 1. The next step is always the same also. Just multiply both sides by y. That never changes. So in the text, what they said was correct. That those, boxes that I showed you. But I can get even more specific with this. Okay. For steps 2 and 3, it's always going to be the same. It's always going to be 1 over y dy dx. And in number 3, you're just going to multiply both sides by y. Okay, multiply both sides by y. Okay, but in the final answer, don't write y. Write what it was equal to. What was it originally? X to the x. So dy dx is x to the x times this new thing. Cancel this out. So 1 plus ln x. So here's the derivative. So the derivative of x to the x is x to the x times 1 plus ln x. So that's the answer that we have there. Okay, and I see we're just about out of time. Okay, so sorry I wasn't able to let you have a question and answer session, but we have to make sure we cover all the material. All right, so that's it, folks. Tomorrow I'll do some more from 3.6, and then I'll give you a quiz on everything, all kinds of derivatives at the end of class tomorrow. All right, that's it for today, folks. So have a good day. We'll see everybody tomorrow. Okay, bye, everyone.